All right. Okay. So last time we talked about the state pattern. Let's do a very quick review on the state pattern. Especially, let's compare the non-OO solution versus the OO solution. Let's see the insight into the two different solutions. Okay, let's see that, and then we'll go to a new pattern with some motivating problem. This is what I would like you to really keep in mind when you try to compare the two solutions, especially later on when you study for the final exam for the state pattern. You really want to understand why a particular solution is not so ideal, so you will really appreciate the design pattern we are trying to introduce to you. Okay, let's see. So over here, don't forget the problem that we are really trying to solve is so-called interactive system, in which case the solution can be formalized using an abstract state machine or like a finite state machine, like what we show on the state transition diagram. Okay? Of course, every problem might have a different diagram that you have to design for yourself, for your application. And now we got two kinds of solution. One is about hierarchical, which is not OO, versus the state pattern, which is OO. Let's see really what the fundamental difference is between the two solutions. Let's have a look at the non-OO solution, which is over here. Okay, over here. It's so-called non-OO, also hierarchical solution, which means at the top level over there, we're trying to execute some interactive session, and which will be subdivided into different stages over here. And particularly for this particular stage called executed states, depending on what the current state is, we're going to do something accordingly, right? Which means we might have to display the current states. We have to read some input from the user and validate whether the input is correct as far as the current state is concerned, depending on what the current state is. And also print out some message to the user and also process to the next state, right? One thing to notice, the main drawback for this solution over here is you have to pass the state information from level to level. Okay, that's really the drawback. Especially, let's say this. For this particular solution, the type for each current state is going to be simply integer, right? And then if you want to execute a session over here, like let's say over here, you have to pass this current state around. Not only that, for all the features we just talked about over here, let's say here for executed states, you also have to take the current states as the parameter. Also for display, for the read, for correct, and for message, for process, you also have to take the current state. And let's go a little bit further. What's so bad about having an integer parameter for each of the feature over there? Just integer, as opposed to objects. How do you tell what the current state is? Should it be state number 1? Should it be state number 2? Up to should it be state number 6? The only way you can tell is to have a long if then else if statement to see if the current state is equal to 1, I'm going to do something. If the current state is equal to 2, I do something else, and etc. Okay? We have to repeat the same pattern for all the features that will take the current state integer as parameter. So that's not good. Okay? And the insight is we want to somehow, rather than having this current state being passed as parameter, we want to shift that conceptually. We want to shift that to be maybe the current objects to call some feature. Okay? That's how we move from hierarchical solution to OO solution. Okay, let's see right away. So in the OO solution, when you declare the same variable called current states, now the type is simply just states. So state is simply a class name that we introduce. Okay, I'm going to show you the architecture in just a moment. And then now, when we just try to call this feature here called execute session, we just have to use to make sure a current state is a context object, which means depending on what the dynamic type is for the current states. So what can be the dynamic type for this current states? It can be any of the descending classes of the state class, right? So depending on how many descending classes you have. And then according to dynamic binding, it's going to execute the correct version of the execute session at the runtime, right? No, nothing to do with that, actually. Yeah, okay. Okay, guys, any question about this so far before I go on to the architecture? So now what you really should understand is how we go from the orange one over there, having current state being integer, move on to current state being of type states in the green one. That's really the main insight you want to get. Okay, we'll get, ask me again once I go over the architecture. Okay, so the question was, in the case of the non-OO solution, if we are trying to add a new state, as we discussed in detail last time, what would be the consequence if you try to add a new state in this particular non-OO solution? Well, the consequence would be you have to add an explicit else-if statement for every feature that would take the current states as the argument, right? That's the catch, which is not good. That violates the so-called single choice principle, right? Because there'll be multiple places you have to modify. Single choice principle. Okay. So now let's go on to the OO solution and let's see how that can solve the problem. The main idea is dynamic binding somehow corresponds to the if then else statements we have to write explicitly in the non-OO solution. Because dynamic binding is really like implicitly if the current object is an instance of, let's say, final states, in which case they will display the state differently, right? So let's just see the architecture, and then I'll give you one more example. Okay, for the architecture over here, let's go over. So this is the client's, any application, any interactive system, okay? And then we have a client-supplier relation, and as far as the client is concerned, they declare some variable of type states. You can see the state is deferred, which means it's just like abstract. They cannot be used as dynamic type. But any of its descending classes can be used as dynamic type. For example, we have initial states, flight inquiry, seat inquiry, reservation, confirmation, help, and final. So these are all the 7 possible dynamic types for the states. Okay? And as you can see, this is the critical inheritance relation we have over here. That's the inheritance relation. And now, let's compare something over here. One more thing to mention, which you should really review the lecture from last time. You can see all the features at the state level, they're also deferred. You can see all the read, display, correct, process, and messaged. They're all deferred. Okay, I'll make a note. You can see the star over here. They're all deferred. The only feature that is not deferred is called execute, okay, over here. So this is the execute feature that's effective, which means it's being implemented. And this is another design pattern that we talk about, which is called template, right? Which means we include the same template for each state. Depending on which state it is, it's going to call the corresponding feature that's effective in the descending classes. I'll leave the details to you to review the lecture, okay? We don't need to spend more time on that. One more thing to show you, okay, about dynamic binding. Let's say I have the current state over here being states, okay? Let's just try 2 lines over here. If I say creates, okay, creates, and then let's say initial, and then I would say, can I just say CS for current state, okay? CS.make current state. And then I would say current state dot executes. Okay, that's one. Let me use a different one. That may be easier. Let's say just display. And then let me say create again over here. And then let's say we move on to maybe help. And current state dot make. And then you would say current state dot display. And one thing to note, you can see these 2 lines are completely identical. But are they going to have the same effects at the runtime? No. Why not?
Because it depends how they're implemented.
True. Okay, how about this? For the first one, when I say cs.display the first time, which version of the display it is going to call?
The one in initial.
Good, because initial is the dynamic type, right? And the second one? What about second one? From the help, yes. Exactly. Whenever we talk about runtime behavior, it's going to be dynamic type, okay? It's very easy. Just quick review. So at this point, dynamic type is initial. At this point, the dynamic type is help. Okay? That's a very quick review of the state pattern. Okay, so I would suggest when you study the pattern for the project or for the final exam, these are the diagram you want to start with and try to tell a story by yourself to see how we move on from the non-OO solution to the OO solution, right? Okay. For example, in the exam, I might just give you an interactive system similar to the reservation system. I will ask you what would be the right solution for that state pattern. Okay? Also, you should know what the drawbacks are for the non-OO solution. Okay, guys, any questions about this before we move on to a new one? Yes?
Why is it that you comparing like the state is that
Yeah.
each state function has to implement all five,
Good.
single one?
The observation is actually related to your question about, let's say for the OO solution, that will be the last remark. For the OO solution here, remember in the non-OO solution, in order to add a new state, we have to add a else if statement for every feature that takes current states as the parameter, right? But now, what about the OO solution? What would be the consequence if we want to add a single state into the context? Let's say we have a new state called, let's say, payment, let's say. How do I add these states into the diagram, in the architecture? Should I put it as a direct client for application? Or should I put it as a client for states? What should I do if I want to add a new state called payment? Inherit the state, right? So that means I should add it to the package over there. Let's say I want to add a new state. I'll put it here. And then we'll talk about what we should do. As soon as I add a state over here that should be also effective, let me just call it payment. Okay? So now the fact that I want this class to be effective, that means every feature that's deferred from the superclass, which is states, must be implemented. In this case, yeah, I see what you mean. In this case, we have a single place, which is a pay class, that we have to implement all the features in a single place. So single choice principle is respected.
So say I don't want to display anything
That means, okay, if you don't want to display anything for the pay states, let's say, you simply just leave the body empty. Yeah. So the good thing about, okay, let me just draw a remark over here. The good thing about this, let me just put it here. So the pay state is going to be the only place we have to do some modification if you want to add the new states. I will put a remark aside over here. Maybe put it in red. Okay, so I'll put it here. This is the single place to implement all the defer feature from the state class accordingly. When I say accordingly, I simply mean every feature that we put in this particular pay class has to implement it according to the pay, right? Whatever you want to display, what you want to message, what you want to validate, they should be all under the concept of payments, right? That's a single choice. Oh, I hope that answers your questions. Right. Okay, guys, any other question about the state pattern? It's not too bad, right? It's I would say it's a nice pattern. Okay, if you have no question, let's move on to a new pattern. Okay, a new problem. Okay. Okay, so it's called composite design pattern. And right after the composite design pattern, we got something related to it called visitor. That might be the most tricky pattern. Hopefully we can start covering that maybe from Thursday. Okay. Let's talk about composite first. Okay, let's talk about some motivating problem over here. The problem would be, let's say we are trying to design some manufacturing system for computer equipments. Let's say for the computer equipment, we have individual components. We also have subsystems. So what do I mean by that? Notice that I'm choosing the words very carefully here. When I say individual components versus subsystem, subsystem simply means they contain certain equipments, individual components. Subsystem can also contain other subsystems. So you can see this notion here is recursive. Okay? A little like a tree that you learned from 2011. Okay, we'll get there. Now, okay, a computer system is composed of individual piece of equipment. It can be hard drive or it can be CD-ROM, DVD drive. which means hard drive does not itself contain any further components. On the other hand, we also got, and also each components might have some properties or features, like a power consumption or price. That's the price is going to be something we try to focus on for this lecture. Okay, we also got other components, which we call the composites. Okay, it can be cabinets, can be buses, or can be chassis. Well, let's see some diagram in the next slides. Okay, let's just see some diagram over here. Something like this. Okay, you can see that on the top, we got something called cabinet over here. Under the cabinets, we got 3 different subsystems. The first subsystem simply contains a power supply. And power supply is already a basic components. It doesn't contain any subcomponents. On the other hand, we also got the second components over here called chassis. And the chassis over here contains further a hard drive and also a DVD room. Okay? The third subsystem we have is another chassis, which contains another hard drive and also a card, video card, let's say. Right? So this is the kind of the system we'd like to design. That's just one instance of that. Okay? Then now the question is, how do we do that? Right? Okay, that's basically the motivating problem we have. We want to design a system that will allow, first of all, how can we build a tree structure like this? First of all, how we build that. And the second thing is, let's say every equipment that we are talking about, for example, a card, hard drive, and DVD room, they have a feature called price. Okay? For example, let's just make it easy. Let's say every basic parts over here is $100, let's say. And now I go to the top level of the tree. I want to know what's the worth of this particular cabinets. You boil down into adding up all the prices for every individual component that's being contained. It would be 1, 2, 3, 4, 400, right? We got 2 hard drives and 1 DVD room. Oh, actually, it should be 1 card, 2 hard drive, 1 DVD room, and 1 power supply. Each one of them 100, we should get 500. Okay, that's kind of the example. But how do you design some nice pattern for that? Okay, that's the thing we are trying to deal with for this lecture. Okay, okay, are we okay with the problem here? Hopefully that's clear to everybody. Okay, now the challenge really is you have to distinguish between the notion about basis versus recursive, like how you do with recursion back in 2011 or 2030. Whenever you want to solve a problem recursively, you have to think about the base cases, like a hard drive or DVD room, and also recursive cases, like a chassis or cabinets. Okay, that's kind of the problem we are facing. Okay, before I go to different solutions for you, we will need something called multiple inheritance, which is not exactly supported in Java. I think the only thing you can say that's kind of similar to what you can do in Java is you can say one class can implement multiple interfaces, right? But you cannot say one class can extend from multiple classes. You definitely cannot do that in Java. But in IFO, we can. Again, we are not trying to do programming in IFO. We're trying to do design. From the design perspective, this is nice. Okay, let's see some example. Okay, just something you want to get used to, and then we'll see that by using multiple inheritance, how we can design a multiple design composite design pattern to solve the problem. Okay, let's just see multiple inheritance. It's a very easy idea. Let's just go through some example altogether. So multiple inheritance, basically just a class may have more than one parent classes. Okay, but what is that exactly? Okay, let's see one example over here. I will show you the diagram over here. Let's go over some detail here. Okay, the same diagram. Let's say what we want to have. Let's say at the top level we have simply a generic notion about taxpayer. Each taxpayer has address. They have the ID for their tax profile. They have their age. They have a command to see how they can pay taxes from their accounts. Right? That's for the generic taxpayer. But now, because dual citizenship or even multi-citizenship is very common for some citizens. So let's say we have a particular taxpayer whose nationalities are Switzerland and also US. Okay? So now that means we have one class called US taxpayer, and also we have another class called Swiss taxpayer. Okay? So now we have some kind of multiple inheritance. over here. Okay, so let's see how multiple inheritance can be useful. Okay, at the top level over here, we have address, we have tax ID, we have age, and we have pay taxes. Okay, now out of the one, let me say this. Out of the 1, 2, 3, and 4. So we got 4 features at the taxpayer level. Okay, which features you think should always be just one single version without worrying about which nationality this particular taxpayer belongs to? Age, right? Well, age, I shouldn't really matter if I'm a citizen of from Switzerland or from the US. Okay, that's good. So that means we have age over here. I'll just highlight that. What about address? Well, address can be, well, let's say address, you may have a residence address maybe in the US, also in the Switzerland, right? That's why over here, let's say particularly, let's see for address over here, you can see now this notion here is a little bit informal, which means rename. That means at a US taxpayer level, we are inheriting this particular address feature from taxpayer. But now we're going to rename that into US address. In some way, we are duplicating. We're duplicating this particular feature called address at the US taxpayer level, and we call that US address. Similarly, when we get down to the Swiss taxpayer class, we rename the address to Swiss address. Okay, so far so good? Okay, it's just one example. And similarly, for the taxpayer ID, choose a different color. For the taxpayer ID over here, it can be US tax ID or Swiss tax ID. Okay, so this is only a first example, but let me just ask you something intuitively right away. Okay, we talk about inheritance, so we're going to talk about static type and dynamic type. Okay, now let's say this. According to this architecture over here, let's say I have the following variables. Taxpayer number 1, taxpayer number 2. Okay? If I say taxpayer number 1 is US taxpayer. Okay? And let's say taxpayer number 2 is the Swiss US taxpayer. And every time we talk about static type, we talk about expectation. Right? Let's just test a few. Okay? Now, for taxpayer number 1, what can I do in order to use a dot notation? Can I say taxpayer 1 dot address? Are you sure? Remember what is intuitively yes, because it seems like we can definitely inherit the address feature from the taxpayer. But remember, in order to distinguish between the address with the Swiss taxpayer, we already renamed this feature, right? So that means when we try to say TP1, the address, given that it's a US taxpayer, this is not okay. What would be okay? Well, if we say TP1 dot US address. So this will be okay. Okay? Similarly, this might be even more intuitive. Can I say something like this? Can I say TP1 dot pay taxes? Yeah, exactly. If you look at that, US taxpayer, the only feature you have in the US taxpayer level is you got US addresses, you got US tax ID, you got pay US taxes, and also you got age. These are the only 4 features you have. Okay? So that means this one here, for the similar reason, this one also is not good. Okay? What you should have said instead would be TP1 dot pay US taxes. This will be okay. Okay? Again, we talk about expectation. So to see the expectation, you only have, in the case of multiple inheritance, first of all, you want to see which features are inherited, and also you want to see how they are renamed into. Okay? How can you? No. All right. Okay, now let's see one more. Now I want you to tell me for TP2, what would be the expectation? What can we write for TP2? Give me the complete list. Okay, I can say TP2 dot switch address maybe. Okay, switch address. And I can also say for sure TP2 dot switch text ID for sure. Okay, basically these two. Okay, and also I can say TP2 dot pay switch Texas. Anything else? Age, thank you. That's good. TP2.age. Okay, that's our first example for multiple inheritance. Okay, any questions about this? Yes.
So the accessor can do something like
Say that again. I don't quite get your remark over here.
taxpayer can do a text.
You know what? Okay, I see what you mean. So if you try to compare, okay, the question basically is about this. If you try to compare pay taxes over here, and then pay US taxes, and also pay Swiss taxes over here, right? These three features. I would say this design here is not very complete. I would say pay taxes over here is a little bit vague. You're not too sure which country you're paying the taxes into, right? So I would say if you're really doing your application, you may just want to make this class deferred. Okay, and this should be deferred as well, which means at this level, I don't know what the mechanism for the tax profiling mechanism should be in order for me to pay. But later on, once you know the country in the context, you can now make them effective. Yeah, you're not really trying to do something different, just specializing what you can do in the subclasses. Okay.
Professor, for example, even if we define the mechanism there in the descending class
Mhm.
of US taxpayer, Swiss taxpayer, for example, if I have address methods on both the descending classes,
Yeah.
and if you were to call the address method is US taxpayer.
Okay, good question. The question really is, if I didn't rename, what would happen, right? Let's say this. The problem is this, okay? You know what? Let me try to draw another diagram over here. That's a good question. Let's say over here, we got taxpayer. Okay, taxpayer again is at the top level over here. And then we have things like this. Okay, that's like more like a diamond shape. So this is a US taxpayer, that's a Swiss taxpayer, and that's the US Swiss taxpayer. And your question was, we do have an address feature over here. What you're talking about is, what if we don't rename the address at the US taxpayer level to US address, and at the Swiss taxpayer level to Swiss address? What's going to happen? It's not going to compile because we have some name clashes. The reason being, if you think about it conceptually, if I didn't do any renaming, then this address over here will be inherited verbatim with the name, address. And over here, it will also be the same name, address. But now, both of them will be accumulated to the same class over here. That means we got two versions of the feature that has the same name. So it's ambiguous. That's why renaming must be done in order to resolve the clashes. It's a very classic problem when you try to do multiple inheritance, but we do have one example at the end. Okay? Question?
Professor, how do you rename these features in
iPhone. Yeah, I will show you. Yeah. So you guys are asking me question a little bit ahead, but we'll see how you do that syntactically. No? But conceptually, we should know that. Okay. Conceptually, let me recap the final question we had. So let's say we do have a top, when we have a diamond shape hierarchy from the multiple inheritance, the top class we have a feature which can be address, and we didn't rename. What we're gonna have is we're gonna have some name clashes at this level over here, because the same feature name, first of all, they were accumulated to the two intermediate parent classes, and then they're accumulated to the same descending class. So we're gonna have name clashes. That's why we simply got renaming over here, right? In the previous notion. Okay. But we'll see one more example in just a moment. That's even simpler. Okay. Any questions about the first example? Yes. You mean TP2 dot? Remember TP, oh, can you say TP2? Yeah, of course. Of course. Okay, I think, yeah, that's a good point. Actually, we forgot, right? So, yeah, that's good. So for TP2 over here, it's a Swiss US taxpayer. We only talk about the Swiss side over here. We forgot about the US side. That's what we forgot about, okay? So we should still be able to say TP2 dot US address. And also we can say TP2 dot US tax ID. And also we can say TP2 dot pay US taxes. That's what we forgot about, right? Yeah. Oh, yeah. Yeah, go ahead. The H. The H over here, it should be renamed as well. It should be. You know what? Let me show you that maybe a little bit later. Yeah, it should be. Oh no, I'm talking about TP2 right over here. TP2 over here. Yeah, the Swiss US taxpayer. Yeah. Your question? Yes. Go ahead.
So does this mean that you can't substitute taxpayer with Swiss US taxpayer?
Say it again. You cannot substitute.
You cannot substitute taxpayer with Swiss US taxpayer?
In this case, you know what? About substitution is a little bit more complicated. So I would say we try to avoid this particular substitution. I would say as far as substitution that we talked about before, just assume that there's no multiple inheritance. Okay, it's actually much more complicated. Okay, yeah. I would say we only talk about a particular problem that we can use multiple inheritance to solve, and that's all we care. Okay. No, in Java it's not. You can only implement multiple interfaces, but you cannot extend from multiple classes. IFO you can say in implements and then multiple classes. That's why we're going to show you. Yeah. So now, if you know, in Java, if you try to implement multiple interfaces, you're only inheriting signatures from the method, right? You're not inheriting any code. But in IFO, the multiple inheritance, you can definitely inherit code from different classes, right? Okay. Guys, any question about the first one? Okay. Okay, that's the first example. Okay. Okay, so now let's have a look. This is another example here. So this is actually from the base library. Okay, now let's see this. For example, this is how you can read it. So we got integer. For example, integer is both a numeric descendants. Also is also comparable. You can compare the real numbers, and also the same for real number and also for double. On the other hand, for the string class, it's only comparable, but it's not numerical, right? And also for a complex number, it's numeric, but it's not comparable. Okay, that's just one another example from the IFO base. Okay. All right. So now let's go on. Now here is the question: how can we make use of multiple inheritance to solve this problem here conceptually? Okay. So, let's say we have let's say each window. You can think about each window is simply like a rectangle. For example, we've got a yellow window over here, which is very big, which contains a blue window over here. And the blue window also contains a green one, and the green one contains an orange one, etc. Which means the window itself can either stand by itself, like the orange window over here, or it might contain other windows, like the yellow one here. Okay? So now, how do we somehow use multiple inheritance to model this? Okay, that's the question. And this will lead us gradually towards the solution for composite pattern. Okay, we'll gradually go there. But now, how do we solve this problem here, conceptually? I'll give you a little bit hints. Let's say these are all the features for the window. We may have heights for the window, width, x position, y position. We can change the width, we can change the heights, we can move the window. We can now see what's the parent window. For example, you can see what's the parent window for the blue one over here, the yellow one, right? The yellow window, it's like a parent, the containing one. And also you can get the descendant windows. How many descendant windows we have for the green one over here? Just one, right? The orange one over here, right? So that's kind of the idea. You can get a parent window, you can get descendant windows, and also you can add child window into the window itself. Okay, so these are the features we would like to support. What you really don't want to do is to have a Superman class which contains all these features. It might work, but it's not maintainable. So this hint here is to somehow to help you to see, can we somehow divide these features into different groups so that each group represents a single class. And then we can say a window is simply going to implement both classes, right? That's kind of the idea, okay? And it's a very general solution pattern for you. If you want to solve a particular problem, think about what features you want to support. And then once you get a large list of features, think about how you can group them into different groups. And then to see what classes you want to create and use multiple inheritance. Okay? Can you see how many groups can we divide them into? 7? That's too many. Well, of course, on the one hand, you don't want to have a Superman class. On the other hand, you don't want to have too many classes, right? 4. Okay, 4. Okay, 5. Huh? 3, sure. I would say there's no standard answer, okay? One possible answer I would like to present to you only got 2 groups, okay? For example, let's see this. If you see over here, starting from the heights over here, let me just move my cursor over here. Starting from the heights, height, width, x position, y position, change width, change heights, and move. All the features up to here, they kind of belong to the characteristic of a rectangle, right? What about the remaining features? The remaining features, getting the parent window, getting descendant windows, will add a child window. Those features more belong to the concept about creating a tree structure for the window, right? So there are different notions over here. So I would say at least 2. But if you really want to have more than 2, that's up to your judgment, okay? But let's see how we can go with just 2 groups. Okay, so now we are separating between graphical like a rectangle features and hierarchical features. Let's see the class decorations over there to get some feel about the syntax, and then I'll show you some tests. Let's see how it's going to happen in the runtime, and then we'll go to composite pattern. Okay, so we got enough warm up for the multiple inheritance. Okay, let's say we have one class over here called rectangle. So this class contains all the graphical feature for rectangle. So we got width, heights, x position, y position. We got constructor make, which will give the width and heights, although change the width, change the heights, and move. Okay? Just one single class. Let's say we got another perspective, which is to have this one is a little bit more challenging. Okay? This one here, we make it generic, which means it doesn't matter what the components for the tree is. It can be window, it can be accounts, it can be Sudoku, right? It can be anything you like. Okay? Now, let's say for the tree class over here, we have parents, we have descendants. You can see that, hopefully you don't have too much trouble of understanding this. We are saying that the parent is simply just another component for the tree, just another subtree you can think about. And then for the descendants over here, it's just going to be a list of certain components like a tree. Okay? And then for adding a child, we simply add a subtree, basically. Okay? And now, how do we combine the features of these 2 classes together? If you want to translate this literally into Java, it's not going to work because you cannot extend more than 1 classes in Java. Okay? But in IFO, you can do it. Okay? This is syntactically, it's very easy. We simply say we have a class called window over here. We have a class called window, simply inherits from 2 classes. You just have to separate them by space or new line. I would say typically new line with the same indentation will be better. So window is basically a subclass of both rectangle and tree. And then here we instantiate G by just window itself. And then we can also add a new window as a child, right? Okay, that's about the decoration. Questions so far? Let's see a very simple test and see how we can get an idea. And then we'll get to the composite pattern. So that will be some test feature to look to. So I would say let's go on to iPad over here. I would say don't struggle too much with exactly how these are implemented. It's just to focus on the ideas. Okay. So now let's say this. What we are trying to do here. This line here, we're trying to create a new object called W1. And here we're trying to create a new object W2, W3, and W4. Okay? So now, let's just see a few things over here. When I say W2, how about just, let's have a look at this line, just this line over here. When I say W2 dot add W4, let's try to analyze this line just a little bit. Dot add W4. Based on what we learned about polymorphism compilation rule, should this line compile? Whether that should compile or not, we should look at the static type. Agree? So now, first of all, I would like to look at the static type for W2. Window, thank you. Okay, now, what features can we call on an object W2 of static type window? Basically, yeah. Yeah, we can call features that are inherited from all the superclasses, right? In this case, we got two superclasses, right? Yeah. Yeah, so over here you can see for window over here, basically inherits from rectangle and from the tree. So that means any feature from these two classes, let's say there's no renaming occurring. Let's say there's no renaming, no clashing. In which case, you can call any feature from rectangle. You can also call any feature from tree. So now, does this add make sense over here? It makes sense because add is exactly from, oh, actually, you know what? I should fix the typo. I meant to say add rather than add child. Okay, except for that, okay? This is a typo, okay? It should be add. That would make sense because now the tree in the tree class, no. What I meant, that's not a typo, sorry. I'm contradicting myself. The add over here is okay because we do have an add feature over here at the Windows level, okay? This add is fine, sorry about that. And now, what about the argument over here? W4, would it compile? What's the static type for W4? Window. And what's the formal type that's expecting? Window. So I'm okay. Okay, so we're fine for that. Okay, just a little bit practice over there. So now let's see. We will see actually examples similar to this, like adding children to the tree a little bit later, but I just want to give you a very quick intuition. For example, what we can have is something like this. Okay, let's say over here, first of all, we are going to use W2 that add W4. What that means is conceptually, we have W2 over here, like a window, the blue one. And then when we say add W4, what that means is we're going to add, let me just write it down. You can think about this is W2, okay? When we are trying to add W4 as one of its children, okay, that's like a subtree. So what we're doing over here is we have W4 over here, okay, like that, one of its children. And what about this line here? When we say W1 dot add W2, okay? Basically what we're doing is we're going to do add W2 into W1, right? So what we got is W1 over here, and then we're going to have W2. Well, actually we're adding W2 as one of the children, so the right way to draw this would be basically like this. Don't you agree, conceptually, right, for that line, okay? We're adding W2 as also a subtree of W1 as a child. And finally, we're also adding W3 into W1 in parallel to the blue one. So that means we're going to get something like this. So that means we also get W1 containing W3 also as a sub-window. So that's kind of the window we are creating, okay? So don't worry too much about the implementation details for this one here, but just focus more on the tree structure over here that we're trying to create. We'll see more concrete example when we talk about composite pattern. But this is kind of the multiple inheritance you want to get used to for your purpose over here for this course, for design. Okay. Again, the pattern is as follows. Every time when you want to figure out what to put in a single class, before that, think about all the features you would like to support. Maybe you got 100 different features. And then think about what these features can really be grouped into different categories. Each category should be a different class. And then think about what kind of multiple inheritance relationship you can support among these classes. Okay? That's kind of the pattern. You can try to follow through. Okay, that's about the second example. Now, finally, for the multiple inheritance, final thing I would like to say about name clashes. Okay, but actually we already have gone through this. Let's say we got A and B being the superclasses for C, and do we have any problem over here? We do, right? Because now foo is actually going to be inherited twice into C. So we do have it disambiguates. Okay, so we do have a problem over here. We do have a problem. So now, how do we resolve this in IFO? Now, back to the original question. As easy as that. So now, let's see the syntax here. So now I have class C over here inherits, first of all, A. After say A, we say rename, which is a keyword. Rename the foo feature that's from A into fog. And then we say B, rename the foo feature here from B into zoo. Okay? Of course, don't memorize the syntax. You just want to copy and paste and use it. Okay? Don't memorize it. You also wouldn't be expected to write something like this, okay, on the exam. Okay? But just understand the concept here. Okay, so now let's test your understanding. Yes? Yeah. You mean on the iPad or the slides?
I think on the slides.
Okay. This one?
No.
Before that?
Yeah, right here.
Yes.
So we aren't redefining make window. So extends it from rectangle.
Rectangle, yes. You know what? I didn't really put anything like that. Yeah. You can imagine, how about this? Let's make it simple. So you got to define the make feature somewhere, right? So you can say, maybe we'll simply define the make in the window class. Yeah, yeah, yeah. Good. So now let's see this one here. So now let's do a little bit test, okay? Now given that this is the architecture we have, also you have the IFO code. So now let's say this. Now we're gonna see different feature call over here, okay? Think carefully, okay? So now let's say O is declared of type A. That means the static type for O is A. Which one can we call? Which one can we not? So now, basically, given that O is of static type A, can we say O.foo? Can we say O.fog? Can we say O.zoo? Yeah, which one compiles? Which one doesn't? How about which one does not compile? Fog and zoo? Okay, sounds good. That's good. Fog and zoo is not good. What about if O is of static type B? Same thing, right? Okay, it's static type B. That means fog and zoo is actually further down in the hierarchy, so they don't exist. But notice one thing, be careful. At the runtime, you can see that given that A and B both support the foo, that means you want to see which version will be called depending on the dynamic type. Okay? Yeah. Okay, what about the third one? Can you call foo? No, because foo has been renamed already, right? It's like in the Swiss taxpayer. You cannot say pay taxes anymore. Okay, very good. You get the idea. Okay, that one is only you can say fog and zoo over here. Okay, that's all I want to say about multiple inheritance. Okay, so now we'll see how we can apply this usefully for the composite pattern. Unless you got questions. You can cast A to C, yes. Yes. Well, it's a descending class, it's like downcasting. But I would say, you know what? I would say make it simple because multiple inheritance has its own rules for type checking, extended rules. Let's not get there. I would say in the exam or for the rest of the course, whenever we talk about polymorphism, dynamic binding, you can still apply, you can see there's no multiple inheritance. Okay. But unless it's very obvious. Yes. No, actually, it's more about not just implementation, it's about the names of the feature. Because if you did not rename the foo from A and B, in which, oh, you know what? Oh, yeah. Oh, you know what? Let's see some interesting case over here. Okay. Let's say this. In this case, I simply rename like this. I simply say rename this foo over here to be, you know what? I just forgot. Foo to fork. Okay. So foo to fork and also foo to zoo, right? This is what we did previously. This will also work. Let's say this. I can choose to rename only one of them as far as resolving the name clashes is concerned. For example, I can say, I only say rename. Let me just write it down completely. You can say inherits A, in which case we don't rename anything. And then we'll say inherits B, rename foo as zoo. And this will also be okay. Because now, what can we call? Let's say if we got object C of type C. So now what can we call in this case? Can we call OC.zoo? Of course we can. That's been renamed too. Can we call OC.foo? Yes, because that one is simply talking about this particular foo. Okay? Yeah.
Is it just the name by itself, or does it depend on method signature?
Just the name itself. Remember in IFO, let's touch that very lightly. So in Java, you can have the same method name but with different signatures. It's something called overloading, right? But in IFO, you cannot have features with the same name, even if they have different signatures.
Oh, so you can't have full taking in
No, you cannot.
a like a string.
No, you cannot. It's just a language design choice they make. Yeah. Okay. Okay, guys. Any question about this? We okay? Yes. Are you talking about this slide here or the previous one? The previous one? The third row you're talking about? This one here, right? Okay. So O is of type C over here, right? That means we are at this level over here. At this level, there's no existence about foo anymore because foo from A has been renamed to fork and foo from B has been renamed to zoo. Right? So foo is not existing anymore. That's after renaming. In the other one, that's okay because in the other example I just gave to you, in that one there, because the foo from A was not renamed, we only renamed the foo from B into zoo. Right? But in this case, we also have no name clashes, so that's fine. All right? Good. Okay, guys. Okay. You have another class. Okay, you're talking about, okay, the question was, let's say we got another class D over here, which also inherit from A and B. Okay, sure. Yep, interesting question. Like that. Okay, now I would say since D has nothing to do with C, right? Agree? That means, yep, you are subject to the same clashes that we faced before. So now basically for D here, you are still inheriting foo from A and also foo from B. You have to make sure there's no clashes. You got to rename at least one of them, at least one.
Let's just assume that A and B doesn't have those name clashes, and would D actually be able to rename the same methods that we
Oh, actually, you know what? Even if there's no name clashes, you may still want to rename. It's okay. For example, you can renaming simply just renaming, right? You can rename as whenever you like. For example, let me just say F and also G over here, right? I can say inherits A and then rename F as H. And also you can say inherits B and then I will rename G as I. Right? You can definitely do that. You don't have to do renaming just for the purpose of resolving the name clashes. You can just rename for your modeling purpose. Okay. Good. Any other questions? Yes.
Because if you have like multiple features that we need to rename, so how does that work in terms of like syntax?
Multiple. Oh, if you got multiple features, okay. Good question.
Like the taxpayer example.
You know what? That's a good question. Let me try to remember. Okay, let's say let me just draw a new diagram. Let's say I got A here, I got B here. Okay, so now for B here, I would say inherits A, right? And let's say we got F and G, for example, right? I can say rename F as H. You know what? I better check the syntax for you before I say that. But you definitely can rename more than one feature from the class. Okay, guys, I will promise for this part here, I don't want to give you something that's wrong. Okay, I'll give you the syntax, but I'll post it on the Moodle. Okay, yeah. But conceptually, you definitely can rename more than one feature. I just got to check the syntax. Any other questions about multiple inheritance? Yes. I'm not saying you cannot. I would say, for our purpose for the design pattern, the case for dynamic binding will be quite straightforward. We can still apply that same idea. I'm just saying that there might be some corner cases which are kind of tricky, which I don't want to get into for this course. That will involve just maybe another series of lectures which we can afford for this course, right? Yeah. Okay, questions?
It's a good question. So for example, let's just say for the new class that you maintain, right?
D, class D.
B, right?
In B.
Let's say C inherits from A, right?
Okay.
And there's another class that inherits from C. Let's call it D.
Okay.
D also inherits from A. D is also inherits from A.
You're basically talking about, can we have something like this? Let's say I just call it E. And then over here, you're saying that E inherits from A, and E also inherits from C. I should really try by myself, okay? But somehow, I would say it's unnecessary. I tell you why. Why is it unnecessary? Because the fact that you try to, it's a very valid question. Okay, guys, the question was, what if I have a new class E, which inherits from C, and also inherits from A? My first response to this would be, why would you do that? Because it's unnecessary. Because the fact that we have over here, let's say E inherits from C, also C inherits from A, implicitly E inherits from A. So you don't have to emphasize that again.
For that example, it works out a little bit differently. Like if you have C that inherits from A, and the next one, the one that you do with the bottom left. If you have C that inherits from A, and you have a class D that inherits from A and C. Oh yeah, it's
Yeah, let's not worry about this example here, okay? Yeah, let's focus more on the simple one. That'll be enough, okay? Okay, let's now go back to our motivating problem there, okay? So now we're gonna talk about composite pattern, okay? So now, for the composite pattern, I will go over this particular slide in just a moment. I want to go to the pattern itself, okay? And as usual, before I introduce the solution to you, let's see something that's not so ideal. It's like before we see the state pattern, I show you the hierarchical solution, okay? The same thought, okay? So now let me go there, first of all, and I'll go over this slide maybe either end of today or beginning of Thursday, either way. Okay, this is our design attempt number 1, okay? This is not a composite pattern yet. And this design is not too bad, I can tell you. It might be working. However, we want to criticize about it as much as possible, okay? I also got some sample tests over there written for you. But let's go over this design here. Because the actual composite pattern is very similar to this. There's only some minor difference, but fundamental difference. Let's see. Let's see what we can understand. Again, I hope that you can acquire the technique to say, given the architecture of the design pattern, we can already predict what's going to happen at the runtime. You don't necessarily have to see the code every time, okay? We have a client called main program. We have a client-supplier relationship, and we simply got equipments called E. And the equipments here is simply being deferred. So we have an equipment class, and then, so now we also got another subclass over here called composite equipments. Okay? So that means we got, so card, disk drive, they are not composite. You cannot add any subcomponents to it. So they are direct descendants of equipments. On the other hand, for the composite equipments over here, we simply got classes like cabinets, chassis, and bus, right? Just extra level. And what's more, can you try to tell me how you understand about this client supply over here? When I say composite equipments, if you look at the green arrow over here, who is the clients? Who is the clients? Clients. Composite equipment, right? So composite equipment is actually trying to use equipments. And then the fact that we have a list over here simply means we got a list of equipments for the composite equipments. And the feature name is called children. So now you can imagine that in the class called composite equipments, we declare a feature called children. And the type is simply a list of equipments. Okay, that's how you can reflect back to the code. Okay, make sense? Okay, and now about the composite equipments, how do we support things like adding a child? We can say add a child equipment. Also, we have a children, which is a list of equipments, something like that. Okay. Now, these features also we have a feature called price. Okay. Now, these features are all defined at the equipments class. Okay. Now, give whatever thoughts you might have, hold it. Okay, let's see a very simple test, and then I'll take whatever criticism you might have. And so these features, again, they are defined at the equipments level. Okay. Now let's have a look at the test. Let's say we have three variables of type chassis, card, and disk. Card, disk, and also chassis. Okay. So now let's say we have a new chassis, a new card, and new disk drive. And now what we want to do is we want to add a card inside the chassis. We want to add the disk inside the chassis. Everything compiles, I can tell you.
When you have the children's list, what do you mean by that?
We have, you mean, oh, sure. Over here. You're talking about this part here, right? Okay. Okay, let me just explain that quickly. So that means composite equipments being the clients declares a feature of type list, which is over here, okay? And we also have dot dot dot, where dot 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 is the supplier equipments.
Thank you.
Okay, good. Okay, that's more precise. So now let's go back to the test code over here. So I can tell you everything compiles. You can definitely write working code for that. But now, do you see any issue with this architecture over here? There's something I didn't write, which can also compile. I'll give you a little bit of hints. The hint is, what's really written here looks fine. But there's something that can also be allowed by the compiler, but it wouldn't make sense. Think about it, okay? And the composite pattern is going to address exactly that limitation. Let me give you a little bit more hints. Oh, you have an answer?
Is children the list of feature equipment?
Of equipments, yes.
So that means that things that you tend not to be composite equipment can also have children.
So that means you can, okay, that's good. So that's exactly right. So what you said was the children over here basically is a feature that belongs to equipments, right? And somehow this children feature here will also be inherited to card and disk drive. So what's the consequence of that? What kind of, yeah, let me just guide you a little bit. What kind of line can you write for the test case that wouldn't make sense?
CRD dot add
Mm-hmm. Exactly. Let's try to be rational here. That's good. Thank you. Let's consider this line here. CRD, static type is equipments. Does equipment support the feature called add? It does, over here. And then the add feature takes a equipment object, right? And D is exactly an equipment, for sure. Okay, so that means this line will compile, but it does not make sense. How can you add a disk drive into a card? Right, that's the flaw of this design. Because somehow you are putting these two features over here that have to do with composite into the equipment level. That's also inherited to those non-composite features. That's the problem. Okay, does it make sense to you? Okay. Yes. So now you can see that these two features over here, add child and children. So these two features have to do with how you create a composite, like a recursive cases, right? How can you add a subtree and how can you add a subchild to the structure? And somehow these two features belong to the equipment class at the top. That means they will be inherited to, of course, cabinets, chassis, and bus. At the same time, they will also be inherited to card and disk drive, which is not good. That's why. Yeah. Now, how do we solve this? Well, no, actually, there's no multiple inheritance. Actually, you know what? What you just said was we don't use multiple inheritance, but the problem is there's no multiple inheritance here, so you cannot blame it for that. We exactly want to use multiple inheritance for that. Okay, one very quick fix would be, why don't we simply say, let me just use a different color here very quickly. Why don't we say these two features should not belong to the level of equipments? Why don't we simply move them to here? Okay, that's one quick solution. However, I will argue that that solution there is going to work, but not very reusable. Because this kind of a tree feature like add child and children, you want to reuse them for all the other instances for the composite pattern. Because currently we're only doing a manufacturing system. We might be doing another school registration system, which also want to instantiate a composite pattern. In which case, you have to redeclare these two features again. But you want to have a single class that represents this kind of tree feature. Okay? But let's see. Okay, let's see what the composite pattern will look like. Like that. Can you see that? What's the difference? What's the additional class? Can you see that? Composite. Okay? So now you can see that rather than putting these two features right into the composite equipments, I want for future reusability. I factor them out into a separate class. What that means is, if I got two instances of the composite pattern, I can reuse the composite class. One more thing. And the composite class itself is generic, which means T can be any type. It can be equipments, it can be students, it can be maybe whatever classes, right?
So to go back to the previous slide.
Yeah.
The other one.
Yeah.
Remove the method of add child
Yeah. Children.
and composite equipment.
Oh, you see, the problem is the thing is, if I try to move these two features into this class over here, right? You can see the type remains to be equipments and also equipments over here. That means they're very specific to this particular manufacturing problem we are trying to solve, right? But, huh? Well, because now for this particular problem we are trying to solve is about equipments, right? But now in the composite pattern there, we're trying to say the composite class itself is generic, which means you can instantiate the T itself to equipment or any other classes, right? So now, this class over here, this pattern here, is a composite pattern, okay? So the critical part really is two things, okay? I would say when you review this particular pattern, focus more on these two arrows. One is this arrow over here, okay, with the children, which I just explained, okay, a moment ago. And the second arrow you want to focus on would be this arrow over here. One is about client supplier, the other one is about inheritance. The client supplier simply tells you every composite equipment simply got a list of equipments, which can be empty, or as many as you like. At the same time, composite equipment is also a subclass of composite, right? Which means from that end, it's going to inherit the children and add features. Yes?
So you said we could also put children and add into composite equipment, but we're not doing that, so we could reuse the same
Yeah, correct.
system for another scenario.
Okay, right. For example, let me make my, yeah, you're right. So for example, let's say this. Let's say this. Let's say, assume for the moment, let's say everything we have over here, let me try to sketch the idea for you. Every class except for composite is in a cluster called manufacturing. It's a manufacturing cluster, okay? You can see composite is not part of it. So what we can do now is, conceptually, I can have just another cluster over here with many classes over there. And then let's call that many registration, for example. Just another application, which will also instantiate a composite pattern. But now over there, we can also try to have this inheritance relation over here to say that one also inherits from the same composite class. That's what I meant. So we are really reusing all the code in the composite rather than duplicating them for many times. Conceptually, yeah. Hey guys, let's now review what we had before, okay? So everything over here is the same as before. Everything over here is just the same as the previous design, okay? They still compile, they still work. Now, if you look at this code over here, which is what we've said would compile in the previous design, but it doesn't make real sense. Now, if I try in the new composite pattern, I say d.add cart, would it still compile? Well, if you're confused, why don't we look at the static type? Okay? What's the static type for D? Disk, I agree. Which is a subclass of equipments. Does equipments have the feature add? No, because add is only a feature for the composite, just another parent. So this will not compile. So this composite pattern here is very nice. It usefully forbids the basic component to add any components further. Okay? So far so good? Okay, so now one more thing to mention. Now the next step is we want to see how to put everything together. The idea is over here. So now in the equipment class, we got something called price. Okay? So now the idea is every card over here, remember we talked about uniform access principle. This is exactly how we can apply that again. Hopefully that will strengthen your understanding. Now price, it can be either an attribute or it can be a query, right? Either by storage or by computation. Now, without telling you the answer, for the basic components over here, they're going to support price. For all the recursive components over here, the composite components here, they also have to support price. Agree? From the client's point of view, they cannot tell whether that's query or attributes. But now, let's say you wear the supplier's hat. The price in the case of basic components like a cart and disk drive, should it be attributes or query? Similar question. For the case of the cabinets, chassis, and bus, the composite equipment, should the price be query or attributes? Okay, we'll start with the basic one. Okay, for these over here, for these, should it be query or attributes? Attribute, right? Because you can assign a price to each one of them, 100, 200, right? That'll be attributes. Good. What about the price for composite components? Okay, when you say query rather than attributes, that means there's got to be some computation to be completed. What kind of computation? Yeah, so now, okay, good. So now, can you just briefly tell me how you will implement that computation? Mm-hmm. Yeah, just go over every one of them and see what the price is, right? Good. That's exactly right. So now, for example, if given a chassis object, we say chassis the price, and then it's going to go over the list of children, each one of them being equipment itself can either be a basic component or subtree, right? Okay, good. Let's see exactly that. Okay, let's see the code. You know what? This diagram looks a little bit funny. I know. It's not like a combination of architecture and code. But let's go over that. I think that's maybe the most efficient way to present the code. Okay. So now let's put everything together. So notice that the arrows over here looks just the same as the arrow over here, basically. Okay. Let's see. Go over the code. You can see the slides as well. So we have a deferred class called equipments, and we have price over here. Now, uniform access principle tells us just by looking at this from the client's point of view, you have no idea whether that's attributes or query. Okay. And then for the first descending class, for example, just card, one of them, we say it inherits from equipments, and then we simply assign the price to be some arguments, right? So this is storage. On the other hand, let's say we also got another class called composite equipments over here. It inherits multiple inheritance. That's why you see the two arrow over here. So we got inherits the equipments, which means we have to implement the price. But now it is a query because you got a do and end over here. And as you guys said, right, you got to write some loop, let's say across. And then you also have to inherit from composite. In this case, we instantiate the T over here by equipments. Okay, just some detail here. And now one more thing to ask you about. This is the most critical bit to look at. When I say cursor the item the price, and I put a line dynamic binding besides that, that's the most critical part to understand. I will see some diagram in just a moment. At the runtime, let's say I'm going through each component, each equipment in a chassis. What can each component be? It can be a disk drive, which has price being attributes. It can be another chassis, which will be a query, in which case you have to go over all the components for that particular sub chassis, right? That's like a tree. Let me be more precise. How about this? Let's think abstractly. It's more like a tree structure. Let's say it's that. Let's say 100, 200, 300, 100, 200, 300, 200. Okay? Let's say this is kind of the tree structure we have, right? So now at the top level, we have a reference to this particular object over here. So now we want to say, let's say this object is called O. When we say O.price, what it will do is basically going to go over each component it contains, and then gonna say the price for each one of them. When I say price for the first components, it has to go recursively to say, to figure out the price for this component here, I need to figure out the price for each individual components for that particular components, right? That'll be 100 plus 200 plus 300. I got 600. And then for the second one, it's just a base case right away. So that would be just 100. And similarly, for the third component here, it has to go down. And then that'll be this, and then we got 700, and whatever sum it would be. Okay? That's kind of the idea. But now, we want to have a more valid syntax for IFO to show you, okay, at the runtime. Okay? Let's do that very quickly. So now that's what we have over here. So now this part we have gone through already. This part we have gone through already as well. Okay. Again, the most important thing to notice is this price over here. Okay. Let's see, this is kind of the structure we have. I'll see how much we can go through. Okay. Basically, we got car, drive, cabinets, chassis, and bus. Okay. So these are the variables we have. And now we simply create each one of them like this. And then for the basic components, we got 200 and we got 500. Okay. So now I already drew some diagram to begin with over there. Okay. Especially, let's now see that over here. So we have objects of type cart, which is over here. This object over here. Of price 200. That's why you see 200 over here. And also we got a disk drive over here called drive. And also got a price 500. So these are the two objects. Okay. Also we have a bus object. Bus is also composite. So bus is over here and it has a children array. And also we have a chassis object here and also has a children array. Nothing has been connected so far. And also we got a cabinet over here which also has a children array. So what's okay? Okay, let's see what all the different colors over there is going to do. What about the blue one? The blue one over there, when we say bus.add cart, when we say bus.add cart, that means the children's list is going to contain one element that is going to point to the same objects as the cart at the runtime, right? That's the blue one. What about the orange one over here? Well, the orange one, the first one here, we're going to say chassis here, and then the first one is going to point to the bus, right? So that means the first one is going to point to the bus. And then the second one is going to point to the drive. And the second one is going to point to the drive. Can you see the tree structure already? All right? Okay, one more. What about the pink one over here? Cabinets, which is here, you're going to add a child chassis. So that means the first one is going to be point to, chassis over here. That's the tree structure we have. Now, let's look at the final line. When we are trying to execute this line over here to say cabinets dot price equals 700, okay? I can tell you that's true, but let's see very quickly how we can do it. We're starting from the cabinet objects over here, which is more like a root of the tree. And then we say chassis dot, cabinets dot price. Now we're calling a query or attributes. The query, right? We're going to go over each component. In this case, there's only a single component for this particular cabinets. And for that particular component, it's as if we are trying to figure out the price of this particular components. And that component is also composite components. Would it be a query or an attribute call? Query, right? Just further one more query. That means we now figure out what's the price for this particular chassis. What's the price? To figure out its price, we're going to go over both of its components, the first components and the second components. For the first components, it's referring to this bus over here. So what's its price? Again, would it be a query call or attribute call? Query, right? It's composite. That means we're going to go to its only components over here, which refer to a card, in which case it will be attribute, which will be 200. That means we got 200 over here as the first result. And what about the second component for the chassis over here? That will be referring to the drive over here, and that has 500, right? So we got 500. Okay, it's a very quick walkthrough for this. Okay, go over that. We'll continue on Thursday.